All right, so I'm really excited to tell you a story today about working with people all around the world to follow your dreams. So this story actually starts at the DMV. So I grew up in Los Angeles, and when I turned 15 and a half, we went to the DMV to get my learner's permit. And I studied for the written test, and as you probably know, there's plenty of time to read up on all the latest driving laws. So here's one. So you're approaching a railroad crossing with no warning devices, and you're unable to see 400 feet down the tracks in one direction. What is the speed limit? Say it again. All right, so it's a multiple choice question. There's only one right answer, and it's A. So there was one question that I wasn't prepared for, though, and that I didn't know how to answer. Do you wish to register to be a tissue and organ donor? Yes or no? This is a very strange question to ask someone right before they get their driver's license. This is not as simple as just donating blood, right? I need my kidneys. Well, maybe I could donate just one, but this question actually goes far beyond living donation. This question is actually about the fate of your organs after you die. This is a really tough question to ask, and we didn't talk about it in driver's ed. We didn't talk about it in school, and I'd never talked with my family about anything like this before. So to make an informed decision, you really need to gather all the facts. So why do we even need organ donors in the first place? So it turns out that the human body actually has a very limited capacity to heal itself. And you've all experienced this. So if you fall down and you skin your knees, you're going to get a scar. And what's interesting is that actually also happens in your internal organs. So if they get damaged sufficiently, they can't heal themselves, and at some point, you may need to get them fully replaced. So in the 1950s, doctors figured out how to transplant organs from one person into another. And since then, organ transplantation has been a key part of our healthcare system in this country. And look at these statistics. So this is from the Federal Organ Transplantation Network. So if you start here, look at the blue line on the bottom there. So this number of donors, it's remained relatively flat over many decades. And the number of transplants performed is higher than that. The reason that's higher is because every donor can save up to 8 lives. So that's good. But look at that orange line, the waiting list. The waiting list continues to increase at a very dramatic rate. There's a lot of people that need organs. There's actually people that die waiting for organs to become available. So we actually need a lot more people to register to be organ donors. But we're also here at TED to think big about the future of what's possible. And is there another way? Is there a way that we can be architects of our own body, as Larry Smart was talking about this morning? So in one vision for the future of human medicine, and we heard a little bit about this too, this is from the prosthetics industry. It's that vision of the bionic human. So the idea that basically any problem in the body could be treated with a device. So if you need a total knee replacement, if you need a hip replacement, if you need a pacemaker, they're working on retinal implants nowadays. So these therapies have had very dramatic impact on the lives of the people that need them. But there are a lot of therapies that are not possible to be treated with the device. So a lot of organs that get damaged can't be treated. So these are based on, these types of prosthetics are based on plastics and metals. They'll never fully integrate with the body. So if you get them when you're young, they're not going to grow with you. You're going to need to get them revised or replaced later. So there's an alternate vision for the future of human medicine, and it's that of regenerative medicine. And the National Institutes of Health has put forward as their mascot for this idea Prometheus from Greek mythology. Now, Prometheus was chained to a rock and sentenced to have his liver eaten every day. This is not the most optimistic vision for the future of humanity. But what gets the National Institutes of Health excited about this idea is that every day after his liver was eaten, it would naturally regenerate again. So this is the idea. So can we induce or replace organ function? Can we make organs from your own cells and use them to replace organs that can't be treated with a device? So organs like the liver, like the kidney, like the heart, maybe even parts of the brain. So the idea of this theory is that cells are always going to outperform devices in medical implants. And this idea has already had very dramatic successes in human patients. So look at these. This is some artificial skin in the top. There's artificial cornea. There's artificial bladder. And these are already in patients helping to heal them. So we now know materials that will integrate fully with the body. And we can seed a patient's own cells on these materials so you don't get an immune rejection from this. What you notice about these technologies is they're all based on thin sheets of material. So the question is, how are we going to translate these ideas into the solid organs, so organs like the liver. And the real answer is we don't know all the things we're going to have to do to be able to do that. We know a few things, and one of which is we know we're going to need a lot more cells. So we're going to need billions of cells. So if any of you came to the lab, in about a week, we'd be able to teach you how to grow or isolate billions of cells. But the challenge is when you take all these cells and you pack them together in 3D, they're not going to be able to get nutrients and oxygen that they need to survive. And this is a little bit counterintuitive, because if you've ever gone to the deli counter, you may not realize that chicken doesn't naturally grow as a solid sphere of cells and tissue. This is completely artificial. So you have to have some way to deliver the nutrients and the oxygen deep inside this solid mass of tissue. So this analogy, how are we going to deliver oxygen? It's not unlike baking a loaf of bread. So when you bake a loaf of bread, you get a crust that forms. And chemically, that crust is oxygenation. It's getting oxygen from the atmosphere. The entire loaf is too, but the outside always gets more oxygen than the inside. It doesn't matter how hot you make the oven, the loaf is always going to have a darker crust than it will on the inside. So what you realize is actually the solid organs terminology is a bit of a misnomer. So your solid organs are not actually solid at all. They have a very complicated, interconnected, multi-scale blood vessel network. So multi-scale means there's many different sizes of blood vessels all connected together. And this is what is the best highway for delivering nutrients and oxygen to cells. So we have no idea how to make structures like this. So maybe we could do it with 3D printing. We've heard a lot about 3D printing today. So what if we could 3D print the cells and the gel, sort of the supporting material? Could we 3D print that, everything except for the blood vessel network, and could we build up an organ that way? And there's a lot of people working on this idea. It's a very exciting idea, but the problem is that there's a lot of cell types like the liver cells, they don't survive this process too well. So you'd want to make something that contains liver cells to be able to be used for human therapy, but liver cells are actually very fragile cells. So how are we going to modify this? We don't know how to modify the cells to make them able to survive this process. So maybe there's a different way. So we were kind of dissatisfied with this option, and we try to think, looking elsewhere for inspiration. So this is from the Body Worlds exhibit. So this is people that have willed their bodies after they die to an artist who will encase it in plastics and put it on display. So I saw this exhibit. This is a whole organ vascular cast of the blood vessel network in a kidney. And when I saw this, this really reframed the idea in my head. So this is really the structure that we're trying to make. So what if we can make this structure first? Maybe we can make this in a material that would be biocompatible, that would not kill cells. Maybe we can then take even fragile cells, like kidney cells, maybe liver cells, put them around this structure afterwards, and then if we pick the right material, maybe we could dissolve this material out afterwards and then leave a perfusable blood vessel network in there that we could then perfuse with blood, flow blood in, get all the cells enough oxygen to survive. So this idea, how are we going to do that? It was kind of a weird idea at the time. It was kind of kicking around in my head. I had seen a bunch of the 3D prints that were coming off of these, both the commercial systems and these open source 3D printers that we saw in the demos today. And maybe something like this looks something reminiscent of something like a blood vessel network, but these materials are not really suitable for this application. So the whole organ vascular cast, it's an epoxy resin, so it's a very cross-linked structure. You can't really dissolve it very easily. The bioplastics that we saw 3D printed, you can dissolve them in organic solvents. Anything you would use to dissolve these materials, they would just kill your cells immediately. So I was kind of looking around, is there another material? So about a year later, I had dessert. And you should always have dessert. So when I had dessert, look at this, not the flan, but look at this sugar cage that's over the flan. So structurally, it's a very strong material. We know it's biocompatible. It's already in your bloodstream. And we want this to be temporary. We know it's going to dissolve as soon as it hits water. So this is the idea that we came up with. Maybe we can use sugar as the 3D printed material to be in the shape of something like the blood vessel networks. We're going to try to modify a 3D printer to print that out, and then maybe we could dissolve that away, then use that to flow blood and keep oxygen alive and keep all the cells alive that way. So that's what we set out to do. So we have a very big team, both at University of Pennsylvania and our collaborators at MIT. But what I think is also very interesting is that we worked with a worldwide community. So a lot of these open source printers that we've seen today, they're collaborated on by people all over the world. And I've emailed people in Europe, in all parts of the world, to try to understand more about how we can modify this. People have been really willing to help me. And also, we took advantage of our local hackerspace, Hive 76. It's a maker space. It's just like Maker Place here in San Diego. And we just kind of walked in and said, hey, we want to modify a 3D printer, figure out how to extrude sugar instead and use it for biocompatibility studies. And they said, awesome, yeah, we'll help you do that. And that's kind of how we figured all this out. So this is an example. This is how we're 3D printing the sugar structure in the lab at University of Pennsylvania. All the modifications to this 3D printer we put back online. You can download them. You can try it yourself. So we're building up this wall. Remember, all of these sugar filaments, they're going to be dissolved later, and that's going to be the fluidic channel we're going to pump blood through. This is me injecting a gel in there to try to solidify it around the sugar before we dissolve it all. So with the 3D printer, you can make really interesting structures. So it turns out the sugar is actually mechanically, it's a glass. So glass is a mechanical definition, not a chemical definition. So because it's a glass, you can make really interesting structures. If you've seen any kind of glass sculpture work, you can try to make structures like that, structures that look like the blood vessel networks in your body with this 3D printer made out of sugar. So things like many different sizes of channels all connected together, they can all be made pretty easily. So now we're going to mold this into the gel, dissolve all the sugar away, and all of these filaments are becoming this blood vessel network. We can pump, this is human blood now, we're pumping through these networks. And we're trying to keep, basically when we put cells there, we're going to try to keep them all alive. So this is the process that we came up with. So if we think back to that slice of bread, the crust layer that you get there, if you look at a slab of gel, so we're going to make a big slab of gel, it's going to contain millions and millions of cells. If I cut that open, I can show you the activity level and the relative zones of activity of the cells. And just like a slice of bread has a crust, what you see is the activity level of the cells in this structure. It's basically looking like that. You get this outer layer of cellular activity. In contrast, when we make a gel containing these channels that we're pumping fluid through to keep all the cells alive, you can see their activity level completely changes. So it's all based on the vascular architecture that we made with the 3D printed sugar that we molded after that. So we see this kind of as a first step getting towards this. As I said before, there's a lot we still don't know to be able to make organs like this. So how are we going to get maybe these more complicated blood vessel networks that I showed in the beginning? I just want to show here, now you're looking at this in higher detail. So every point of light here is a single cell, and you're looking at more than 1 million cells in this cross-section. So it's really an amazing system. This is using basically panorama software from people's vacation software. That's also open source. We used to stitch all these images together. These are more than 100 microscope images. So to make a much more complicated vascular architecture, this is one idea, and we still haven't tested this. This is just kind of what we're thinking about for the future. Maybe some of you have other ideas, and you'll contribute to this space. We'd love to see that. So maybe we could take this kind of structure that we're scanning this organ, basically like CAT scanning. We can extract the vascular architecture out of that. We can make that into a 3D printed file that we could print on the 3D printer directly. But this structure is very complicated, and there's a lot of artifacts that you get. There's a lot of things in the structure that you wouldn't want to have in the final structure. So maybe we could analyze that architecture and then recreate something like a tree from scratch in a 3D printed material like the sugar to be able to mold that. And so I just want to emphasize again, there's so much that we don't know that we don't even know. So the more that we learn, the more that we realize there's a lot more work to do. So no matter what size of scale you're looking at your organs, there's an enormous amount of complexity, and we don't know which of these components we're going to need to have to be able to make these organs and organ replacements for people. So until that day, I'll be glad to stay registered as an organ donor, and I'm looking forward to the future when no one will ever have to answer this question again. So thank you.